Hello, my name is Joris Gillis. I'm a postdoc at the MECO research group at KU Leuven, Belgium. And in our group, headed by Professor Jan Swevers, we work a lot with optimal control problems in various applications. Some of us work with iterative learning, there's motion planning, there's model predictive control, there's system identification. And a lot of us have produced some research code in parallel to solve optimal control problems for their applications. We solve them mainly by posing them as a large nonlinear optimization problem solved with Casari. But now we set out and try to create a layer on top of Casari that makes it much easier to work with optimal control problems. And that's the software I'll be presenting. And I hope it might be useful for your research or for your teaching activities. So this is the website of Rockit. This is the nice logo. You can install it with a Python pip command. You can try it in the browser. But for now, let's head to a text editor and do some demonstrations of main features of Rockit. So we're in Python world, so I'm gonna from Rockit import star, and I'm gonna create an optimal control problem running with a time horizon of 10 seconds. I'm gonna create a state x, just a scalar state, and I'm gonna say that the state evolves with its derivative being 2. And I'm gonna put a constraint on where the state should be at t0. So I do subject 2 at t0 of x equal to 0. So we start out the state from 0 and see where we end up. So it's an initial value problem for now. We specify solver. Let's use IPOpt. We specify a discretization method. Let's pick multiple shooting, 20 control intervals, and a Rungo-Kutta integrator. Let's see if this solves already. Okay, it runs but doesn't solve because I didn't ask it to solve. Problem is solved, and you see IPOpt iterations going on to solve this optimization problem. Let's store the result. This is like an object that holds the entire optimal solution, and we can do things with it like sample the actual state on the integrator grid. And we get the time series back and a value series back. We can plot these against each other. To make the plotting in Python, I use Pylab. Okay. Blam. So we have the state going from 0 to 20 in 10 seconds. Okay. Let's make the plot a bit nicer. Now you can really see the samples. We can do exponential growth if we say that the right hand side is x. Exponential growth starting at 0 doesn't go anywhere. We need to introduce one patient 0 and we get viral growth. Okay, we can also make the right hand side time dependent. So explicit time dependence is done with OCP.t. You can make an expression of it, like the sine of t, whatever you like. Now at the moment you see the samples, the dots are quite accurate, but in between it's just linear interpolation. We can do better because we use like a high order integrator, Rungo-Kutta, which actually outputs polynomials, and we can use these to subsample much finer. So that's what we'll do next. refine it a lot, and make a new plot. Yups, much smoother. We could also put constraints at the end of the interval. So we could say that we're going from 0 to 1. So like a boundary value problem. Not enough degrees of freedom. Yeah, indeed, it's overdetermined because the slope is fixed. But what we can do is make the slope a variable. So something for the optimizer to figure out. And then it will find a solution. So if you wonder what the slope is, we can just ask it. So what is the value of the slope, please? So it's 0.1, more or less. Makes sense. Instead of variables, we can also work with entire signals, like a control signal. So let's say U is the control signal, and we have a pure integration task. Let's solve it. Slope, yeah. Print should be removed. Right, okay, this is going from 0 to 1, so it's a valid solution. Let's plot the actual controls also in a new plot. So I'm gonna copy this guy and ask the solution object to sample the control signal. And we'll see that it's in fact piecewise constant. So that's like the underlying definition. So why is it still sloping like exponentially or something? It's just sheer luck. It's a valid solution. To make the solution more unique, what you can do is add an objective. So let's penalize the use of a control effort. So let's do the running integral, for example. Popular choice. And then the best thing to do is just to keep steady with the control. Makes sense. Let's make the control problem a bit more interesting. Let's go for a 2-degree system now. Let's say the derivative of x is v, and the derivative of v is something nonlinear, 1 minus x squared times v minus x plus u, for example. We can add more terms here if we want. And let's say that we start x and v both at 0 at time 0. And lastly, let's plot the v state. Wow, that failed. What did I mistype? Let me pick my backup option. Yeah, my backup option, sorry, I must have mistyped something. So you see here the states evolving in some way and the control signal doing its thing. Let's add a constraint. So this is the v state. Let's constrain the v state to be above some number here. So we can add this anywhere. So this is like adding a path constraint to your optimal control problem. See, now it's clipped up to 0.25. What if we give some nonsensical constraint? Let's try this. Say the sine of x bigger than 2. What happens? Infeasible problem. Yeah, might happen a lot by accident. So what are your options to debug this? you could catch this thing and say, okay, show me what constraints are actually being violated. Yeah, we can remove this for a moment. Blop. And now you get like a reference to the exact line in your code of where the problematic constraint is happening. So that's something nice to have. Now, back to this solution. Let's look at the plot in a bit more detail. Let's do the refined thing again. For V, with constraints, sorry. So V bigger than minus 2.5. Okay, and you see, actually, the multiple shooting code is a bit lying to us. It was telling us, you're being satisfied is constrained, but it's only satisfied at the edges of the control intervals. In between, you're violating the constraints. So what you could do is actually give more integrator steps, more than one per control interval, and then you can put constraints on these sub-sampled thingies. So let's just do that. Let's say 4 integrator steps per control interval, and let's also plot these. Okay, so we now have the dots as the control edges. We have the continuous interpolated thing in between, and we have like the 4 steps in between. Now by specifying on the subject2 command the integrator grid, we can impose like more constraints, which should make sure that you stay above minus 2.5. Well, a little bit of violation. Let's look a bit as to how these things are solved. Let's simplify this code. So behind the scenes, this is posed as a nonlinear optimization problem. There is exact derivatives involved. There is a Jacobian and a Hessian with familiar block structure. Now, if you use something else as discretization method, like single shooting, you get a much denser result. Yeah. There's 1/3 method that we implemented, which is direct collocation. Okay. Next thing I want to show is like a non-uniform time grid. So I'm gonna head back to here and say my grid is geometrically increasing. So what does this mean? This means that the distance between samples, or the length of a control interval, is larger at the end by a factor 5 as in the beginning. So this is one of the options you have. Another thing in Rockit you can do is free end time problems. So you can just let the timer run free and maybe make time optimal. So at objective OCP.big T is like the total time horizon. So this is not really a well-defined problem, it seems. Where did I go wrong? Let's add some more constraints. Not really. Oops. I'm trying to make the live experience with the mistakes and all. So now the optimizer chose to have a horizon of only 0.4 seconds to achieve a certain goal. So that just to say you can do time optimal things as well. One last thing I want to show is parametric grids. No, parametric optimization problems. Right. So instead of hard coding this limit, I'm going to make it a parameter. The parameter is something you can change after setting up the problem structure. So let's say set the value of the parameter to minus 2.5. And to minus 3, for example. And you should get a different control signal. Let's say that you start is like the beginning of the control signal. So the thing that you would give as a command in an MPC scheme. And let's print out the value of the starting optimal control for the two different parameters. I need to hide the printout a little bit. So let's say the timings, we don't need them. IP opt should be hidden. Blob. Okay, so for two different settings of this bound, you get two different results. And the thing is that this step is much faster than the first solve. So first solve bakes in the structure, and then you can still change the numerical values. What we also can do is make actual functions, so mappings. So let's make a mapping from the parameter W to the optimized starting control thing. Okay, so I'm almost done. Okay, I need to work on the syntax a little bit. Now it should run. Yeah, let's do a whole sweep. Let's do a linspace from minus 2.5 up to minus 0.6, 20 steps. We pass this vector of W's to our parameterized solver. And let's make a plot. Yeah, so parameterized solutions for you there. Last thing I want to show is cogeneration. Let's change the solver to something that we can cogenerate. So an SQP method with the QRQP solver. We generate a C file, we'll call it par-ocpc. We want to have a main in there. Okay. Blob, what's going on? The printing. Yeah, let's look at the file. So a whole bunch of C code with the main thing in there. So let's just compile it. OCPC, link in the math library, give it some output. So now we have some executable, OCP, run, and let's give it some numeric value, and it will solve the problem for you, all from an executable. Thanks for your attention.